So in this appendix, we are going to work out the position representation of the time evolution operator. The position representation of the time evolution operator is the propagator, and we're going to work that out for the non-relativistic case where we have a free particle. But let's just first start with the general case. So we have the Schrodinger equation, which is given by this. Now, I'm just going to use the bracket notation, then this would be given by ket. So the general solution to this equation, if h is independent of time, is given by psi at time t is e to the power minus I h t divided by h bar acting on psi at time 0. And this operator is what we call u of t, or the time evolution operator. Then the propagator, which is written by k x at time t and at x prime at some earlier time, which we can take to be 0 for convenience, that's given by the time evolution operator, but sandwiched between the eigenfunction or the eigenstate of the position operator. So on the right side, it's x prime. So this is the definition of the propagator in non-relativistic quantum mechanics. So let's just look at this. So psi of t is equal to u of t psi of 0. Let's just look at what it means. So let's just apply x, the bra x from the right. Then, this is exactly a definition of what we call the wave function, which is a function of x and t. So we have the wave function at position x and at time t is given by the bra x ut acting on the ket psi at time 0. But then what we can do is that we can use the fact that this is integrated over all space is just the identity operator. We can use this to introduce here a complete basis of states, but then of course I have to integrate over all of the x prime, and then I have u of t here, and then I can do is I can introduce another complete basis of states here, and then we have psi of 0. And then if we do this, then we'll have to integrate both over x prime and x double prime. So now let's look at this more carefully. So by orthogonality of states, this is going to give me a delta function. So I have dx prime, dx double prime. Then I have delta of x minus x prime. And this thing is the definition of the propagator. So we write it x k x prime t semicolon x double prime 0. And this is going to be psi x double prime at time 0. So now what we can do is that we can use the delta function to do the x prime integral. If you do this, then wherever we have x prime, we have to put x. So we have left over dx double prime, and then k becomes k of x t, and then x double prime 0 psi of x double prime 0. So we see that the wave function at a future time at some point t is given by the integral over the wave function at an earlier time over all of space weighted by the propagator. So pictorially, we can represent it in this way. So suppose this is my time axis, so time flows this way, and this is my space axis. So this is so we have over here, time t equals to 0. And at future, we have the time, say, t. Let's just call this time, time. And here we have another spatial slice like this. So all the points at time t equals to 0 of the spatial slice, and let me label them by the real variable x prime. And here, let me label the spatial variable at time t at x. So now if you want to find out what the wave function is, say over here, what the Schrodinger equation, what this equation is telling me is that I will have to take into account the value of the wave function at every point in space at the earlier time, but their influence on this point is going to be given by this function. So this function represents the the influence that a unit or a delta function wave function has. And then, we basically, what this means is that we add up all these influences over this whole spatial slice, and they all add up to give me what the wave function is at a later time. So this is the meaning of the propagator. So now what we can do is that we can express the propagator in a we can work out in detail what the propagator is going to be for the case where we have a free particle. So for the free particle, the h is the Hamiltonian, and that's given by p squared by 2m. So, so one thing we can do is that we can now look at this thing, and we can use the Fourier integral theorem, phi of x of 0. And the Fourier integral theorem tells us that this would be given by 2 pi h bar, the double integral of phi at x prime 0, e to the power I by h bar, p x minus x prime, and then we have integral over dp and dx prime. Right. So what is psi of x of t? Well, psi of x of t is given by the integral over all x, let's call it x prime, of, say, k, and then x t x prime 0 psi of x of 0. So note that psi of x at time t is e to the power minus I p squared by 2m. This is the Hamiltonian t over h bar. So this is what we have. And this is acting on psi of x of 0. So this is the operator. Now the expression for psi of x of 0 is given by this thing. And what we have is that if you look at the position representation, this is the derivative operator. So this thing can go inside and can act on this. And if you look at this expression, we see that here there is an exponential with e to the power I p h e to the power I px over h. So if you look at this, then it becomes clear that psi of x of t, with this thing acting on this guy, where this expression is given by this Fourier expansion, this becomes 1 over 2 pi h bar. And now we have a double integral, And of course, we will have the usual e to the power I over h bar p x minus x prime. But now we are also going to have, as an effect of this operator acting here, e to the power minus I p squared by 2mt, where p now is just this number p. It's not the operator anymore. And then we'll have an integral over d of p and then integral over d of x prime, but we are also going to have psi here with x prime and 0. So this is the expression we get. So if you compare it with this expression, we find that the time evolution operator k of x of t and then x prime of 0 is given by basically this integral without without the psi. So this is given by I think there is probably some factor of 1 over 2 pi h bar, and there is a integral over p, and then we'll have e to the power minus I by h bar p x minus x prime, and then you have e to the power minus I p squared divided by 2mt. And now if you do this integral, then it just comes out to be m over 2. This is just a Gaussian integral, so hit, there's a square root, and then we have e to the power im x minus x prime squared over 2h bar t. And this is the non-relativistic propagator for the free particle.